All right, let's dive right in. In this explainer, we are going to take something completely invisible, the physics of sound, and make it entirely visible. We'll be using some really incredible diagrams and data straight from our Cambridge IGCSE physics source material. Have you ever actually stopped to wonder how a noise travels from whatever makes it through thin air and perfectly into your ear? Or why some sounds can punch right through solid steel while others are completely silenced by just putting a glass jar over them? Well, today we're going to unpack the hidden physics happening all around you, literally every single second of the day. Here is our roadmap for the journey. We're going to track a sound wave from its very birth, figure out how it travels, calculate its exact speed, see how scientists visualize pitch and loudness, and finally, look at the amazing things happening completely beyond human hearing. Okay, let's start with section 1, the origin of sound. So what's really fascinating here is that whether it's a buzzing cicada, a massive metal gong, or even your own vocal cords right now as you speak, every single sound in the universe begins with a vibration. This image brilliantly shows exactly what that vibration does. When you strike a tuning fork, its prongs rapidly move back and forth. Now, as the prong moves forward, it acts kind of like a microscopic snowplow, squashing the surrounding air particles together. And as it moves back, it spreads them out. It's a continuous chain reaction. That chain reaction sets up two very specific zones in the air. A compression is that dense region where particles are crammed tightly together. A rarefaction is the opposite, the less dense region where they're spread further apart. So the air itself isn't actually traveling from the fork to your ear. Instead, these alternating patterns just pass the vibration along, kind of like falling dominoes, creating what we call a longitudinal wave. But here is where it gets really wild. Because sound absolutely relies on these particles bumping into each other to pass the energy along, it desperately needs a physical medium to travel through. This perfectly explains why an electric bell ringing inside a sealed glass jar goes completely eerily silent when you pump the air out to create a vacuum. You can literally still see the bell's little hammer vibrating away, but without air particles to carry those compressions and rarefactions, the sound just ceases to exist. There's no medium, so there's no sound. Let's scale that exact concept up to a planetary level, because this is mind-blowing. Our sun is essentially a giant sphere of continuous, massive nuclear explosions. If sound could travel through space, the Earth would be subjected to a continuous, deafening roar, like it would be unimaginably loud. But because space is a vacuum, totally devoid of particles to carry those huge disturbances, we are perfectly protected by an immense, silent barrier. Moving on to section 2, let's see how all this particle bumping translates into the mathematics of speed. We've all experienced this during a thunderstorm, right? You see a massive flash of lightning light up the sky, but then you're waiting 1, 2, maybe 3 seconds before the thunder actually rattles your windows. So why the delay if the flash and the boom happen at the exact same time and place? To answer that, we have to look at the absolute speed limit of the universe, light. Light travels at a staggering 300 million meters per second. Sound, on the other hand, it only travels at roughly 330 meters per second in the air. That means light is roughly 1,000,000 times faster. So the visual information of the lightning reaches your eyes almost instantly. But the sound wave, it's trudging along, taking about 3 seconds just to travel a single kilometer. So next time there's a storm, divide the seconds between the flash and the boom by 3, and you'll know exactly how many kilometers away it is. But check this out. The speed of sound isn't fixed. It drastically changes depending on what it's traveling through. In air, like we said, it's about 330 meters per second. But in water, it jumps up to 1,500 meters per second. And in solid iron, a massive 5,000 meters per second. It seems kind of counterintuitive, right? But remember those dominoes? Because particles are packed so much closer together in solids than in liquids or gases, those vibrations can be passed from particle to particle far more easily and way more rapidly. All right, on to section 3. How do we actually visualize these invisible waves to understand pitch and loudness? Since we can't see air compressing, scientists use an instrument called an oscilloscope. By using a microphone to convert a sound wave into an electrical signal, the oscilloscope produces a trace line on a screen. It brilliantly translates those invisible air squashes into a clear visual wave. If you play a pure, simple note, you get this beautiful, perfectly smooth repeating curve. When we look at that wave on the screen, it reveals two absolutely vital measurements that determine how we experience a sound. First is amplitude, which is the height of the wave from its flat middle resting position. Amplitude determines the sound's loudness. Second is frequency, which is the number of complete waves happening every single second. Frequency determines the sound's pitch. Frequency is such a big deal in physics that we give it a specific unit, hertz. 1 hertz literally just means 1 complete vibration per second. So, if you want to remember the golden rule for visualizing sound, taller waves mean a larger amplitude and a louder sound. Meanwhile, if you see more waves tightly packed together on the screen, that means a higher frequency, which translates to a higher pitched squeak in your ear. Which brings us to our final section, beyond human hearing, exploring the hidden frequencies we can't even detect. Our human ears are incredible, but they definitely have limits. A healthy young person can generally hear sounds ranging from a low, bassy rumble of 20 hertz all the way up to a piercing 20,000 hertz. But as we age or, go to too many loud concerts, the delicate sensory cells in our ears start to wear out, and those highest frequencies, they're always the first to go. Actually, there are devices called mosquito alarms that exploit this exact biology. They blast out a pulsing tone around 17,000 hertz. It drives congregating teenagers absolutely crazy, but it's completely blissfully inaudible to older adults walking right past them. But what happens when frequencies are pushed past that 20,000 hertz limit? We enter the realm of ultrasound. Now, humans are entirely deaf to these high-speed vibrations, but the animal kingdom sure isn't. Dolphins use ultrasound to communicate and navigate through the dark ocean, and dog trainers use special ultrasonic whistles to give commands that we humans can't even hear. And, of course, engineers have figured out how to harness this hidden realm of sound, too. They use a technique called sonar. Basically, a ship sends a pulse of ultrasound straight down into the water and then times exactly how long it takes for the echo to bounce off the seabed and come back up. It's a genius way to map the ocean floor. Let's actually put this into practice, because the math is pretty neat. Say a ship sends an ultrasound pulse and hears the echo exactly 3 seconds later. We know sound in water travels at 1,500 meters per second, so 1,500 times 3 gives us 4,500 meters of total distance. But wait, here's the trick that catches people out. That pulse had to travel all the way down to the bottom and then all the way back up, so we absolutely have to have our final calculated distance. That means the true depth of the water is 2,250 meters. And this exact same echo reflection principle works for the human body too. Doctors use it to safely look inside us. By sending ultrasonic waves into the body and having a computer analyze how they bounce off the boundaries between different internal tissues, they get highly detailed real-time images. It's how we monitor a developing baby, and the best part is it uses absolutely no harmful radiation. So that brings us to a really fascinating close. Think about it. Every conversation you've ever had, every song you love, every alarm you've ever heard, it all exists solely within that tiny 20 to 20,000 hertz window. It really makes you wonder, doesn't it? Just how much of the universe's grand symphony are we entirely missing out on? It's a perfect reminder of why studying physics is so absolutely essential. It gives us the tools to reveal the hidden realities of this incredible world we live in. Thanks so much for joining me on this explainer, and keep questioning the invisible forces around you.